What if I told you that your automated tests might be lying to you? Not intentionally, but here's the thing. When AI generates your code and your tests, they can share the exact same blind spots. Your tests pass, your code ships, and then production breaks. Today I'm going to show you a different approach. One where your requirement specifications literally become your tests. No manual mapping from requirements to tests. No blind spots. Just properties that prove your code works. So, let's dive in. This is about the evolution of testing, going from spec-driven development to property-based testing, or PBT. Here's what we're solving. How do you create a direct, verifiable link between requirements you specify and what your code actually does? We're going to use a traffic light controller as our example throughout this video. And here's the safety requirement for traffic lights. Two directions must never be green at the same time. Sounds simple, right? Cars going north and cars going east should never both have a green light. That would be bad. But testing this correctly? Way trickier than you'd think. Okay, here's the core problem, and I want you to really think about this. If AI generates both your code and your tests, how do you know either one is correct? Look at the ideal flow. You've got a spec. From that spec, you derive tests. Those tests validate your code. The tests validate code part? That works great. That's what testing frameworks do. But here's the gap hardly anyone talks about. How do you verify that your tests actually match the spec? There's no automation for that. A human has to manually check every single test. And that means answering two annoying questions for every test. Question 1. Which requirement does this test even apply to? Look at this code. Is this testing our safety rule? Is it testing state changes? Timing? Who knows? It's totally unclear. Question 2. Does this test actually verify the requirement? Our spec says two directions must never be green at the same time. But this test, it only checks that north can turn green. This test passes even if your code lets both directions go green. The test is basically useless for our safety requirement. And here's where it gets really scary. When AI generates both code and tests from the same understanding of the spec, they share the same misunderstandings too. If you have a bug in AI's interpretation, you get buggy code that passes buggy tests. Everything's green in CI, and we ship it, and then something goes wrong in production. So what's the fix? What if your specifications could directly become your tests? That's property-based testing. It creates an automated, traceable link from requirements to verification. No more manual mapping, no more shared blind spots. Let me show you exactly how this works in 4 steps. Step 1. Natural language requirements. You start with plain English. Your acceptance criteria. Two directions must never be green at the same time. Clear, human readable, but you can't run it as code. Step 2. Textual properties. Now transform it into a universal statement. For any sequence of operations at every point in time, at most one direction has a green signal. See that phrase, for any? That's the key. Properties describe behavior across all possible inputs, not just examples, everything. Step 3. Executable property tests. Now it becomes real code. This uses hypothesis, a property-based testing framework. That given decorator generates hundreds or even thousands of random operation sequences. And for every single one we check, is there more than one green light? Step 4. Minimal counterexamples through shrinking. This is where the magic happens. When a test fails, it doesn't just say, failed. The framework found a failure with 47 random operations, but then it shrinks that down to the minimal case. 2 operations. That's it. That's all you need to break the safety rule. By shrinking down the operations that result in breaking the safety rule, the bug is now obvious. Now let's go deep on shrinking, because this is what makes property-based testing so powerful. You run your test. It fails with some complex input. 47 operations, emergency modes, timing changes, transitions everywhere, a complete mess. How do you debug that? You don't. You let shrinking do it. Let's break the shrinking process down in stages. Stage 1. The initial failure. Hypothesis finds something that breaks. 47 operations, including emergency mode activations, timing config changes, a bunch of state transitions, and somewhere in there, a safety violation. Stage 2. Shrinking starts. Hypothesis asks, do I still fail without the emergency mode stuff? Yes. Remove it. Do I still fail without the timing changes? Yes. Remove them too. We're down to 12 operations. Stage 3. Simplify test input values. Numbers shrink towards 0. Complex configs become minimal. 4 operations left. Stage 4. Arrive at a minimal example. 2 operations. That's it. 2 consecutive transitions to green. No check for existing greens. Bug found. The fix is now obvious. Before setting a light to green, clear any existing greens first. From 47 confusing operations to 2 obvious ones. That's shrinking. Now, let me show you how property-based tests work in practice, using spec mode in Kiro. Kiro's spec mode writes requirements using the ears notation or easy approach to requirement syntax. Look at this traffic light requirement. When a signal transitions to green, the system shall ensure no other direction has a green signal. Ears notation provides structured, constrained natural language templates that reduce the ambiguity inherent in traditional requirements writing. This structured format enables formal reasoning, and Kiro does this in 3 steps. First, Kiro writes requirements in ears format. Then it extracts testable properties from those requirements. Finally, it generates and runs hundreds or even thousands of test cases, automatically using property-based testing libraries, such as Hypothesis for Python. Here's what a property actually looks like in Kiro's design document. See how the property is structured here? For any sequence of operations, state transitions, emergency modes, timing updates, at every point in time, at most one direction should have a green signal. 3 things to notice here. First, that for any tells you it's a property, not just an example. Second, it links directly to requirement 2.3, full traceability from tests back to requirements. Third, it connects to actual executable test code, requirements to properties, to tests, to code. Every link is explicit. Now here's where property-based testing really shines against traditional unit tests. Each cell you see here represents a unique combination of operations. Watch as property-based testing randomly samples across the entire input space. Because the human doesn't have to explicitly write every test, there's no bias and no blind spots. A human might write 5, maybe 10 test cases, limited by imagination and time. Property-based testing can generate over 1,000 tests, exploring edge cases you'd never think to check. That red cell? That's a failure found through property-based testing, a bug that traditional testing might have missed. When property-based testing finds a violation, it doesn't just fail. It shrinks the failure down to a minimal counterexample. Kiro then gives you 3 paths forward to fix the failure. Fix the spec. Maybe the requirement was incomplete. Fix the implementation. Maybe the code doesn't match intent. Kiro can even auto-fix this. Or fix the test. Perhaps the property was overspecified. Kiro gives you control by allowing for human judgment combined with automated testing. Let's put unit tests and property-based tests side by side. In traditional unit tests, you test specific examples you thought of. You're limited by your imagination and biases. You miss edge cases you didn't anticipate. There's an indirect connection to requirements, and when unit tests fail, you get one specific case. In property tests, you test universal properties across all inputs. By leveraging random generation, tests are not constrained by human bias. You find edge cases automatically. There's a direct link to specifications. And shrinking gives you minimal debuggable examples of failures. Unit tests aren't bad. You should still write them. But property tests give you something fundamentally stronger. To summarize, here are 6 reasons you should care about property-based testing. 1. Direct traceability. Every property maps to a requirement. No more questions like, which test covers this? Every link is explicit. 2. Bias elimination. Random generators test inputs you'd never think of. They find bugs hiding in the corners. 3. Minimal counterexamples. When things break, you get the smallest possible failing case. Debugging becomes fast. 4. Tight feedback loops. AI can use these counterexamples to auto-fix code. The examples are perfect for automated debugging. 5. Executable specs. Your properties aren't just documents, they're running tests. Specs can't drift from reality because they are the tests. 6. Stronger guarantees. Testing entire input spaces beats testing a few examples, every time. Before we finish, here are 3 patterns you can use today with property-based testing. Pattern 1. Invariants. Something that must always be true no matter what operations happen. In our traffic light example, after any sequence of operations, this must always hold true. Pattern 2. Round trips. If you encode then decode, you should get back what you started with. Great for testing serialization, compression, encryption, anything with an inverse. Pattern 3. Idempotence. Doing something twice or more equals doing it once. Critical for APIs and distributed systems. If a request gets retried, things shouldn't break. Once you start seeing these patterns, you'll find them everywhere in your property tests. So here's the takeaway. Property-based testing validates universal properties across entire input spaces. It creates a feedback loop between what you specify and what you build. Instead of asking, does my code work for these examples? Ask, does my code satisfy these universal properties? Pick one function, write one property, see what it finds. I bet it'll surprise you. If this was helpful, hit that like button. Subscribe for more content on AI-assisted development and testing and adventures with generative AI. Drop a comment. Have you tried property-based testing? What did you find? See you in the next one.